This is Philippe with a third video about turbulence modeling and simulation. In the first I had a visual introduction to turbulence and its physics, then the basics of turbulence modeling. Today I want to discuss steady turbulence modeling versus turbulence-resolving simulations. For a little bit of perspective, the basics of turbulence modeling we've been working at for about 100 years, and turbulence resolving simulations more like 15. Okay, so the basis of doing turbulence resolving instead of just straight steady turbulence modeling. Well, first of all, direct simulation that you saw a few of is completely out of the question based on cost. So two common reasons for unsteady simulations are if the geometry is time dependent, like you can see the blade is moving. So, and the second one is if steady turbulence modeling is not accurate enough, like here in the wake of the body, and this picture, NASA picture of an air taxi. Now, why it gets complicated is that industrial CFD often needs different treatments in the different regions of the same run. This is all due to high Reynolds numbers, and the thin attached boundary layers on the blade or on the body are best with RANs, and the regions of massive separation essentially need the turbulence resolving 3D unsteady simulations. I claim that this is a century of hybrid RANS LES methods. That is, we will be doing it for many decades. The principle was established in 1997 with the DES method, and we had our first 3D results in 1999 on a circular cylinder. Now, many other hybrid methods followed. Often, mostly people won't have their own name. But the principle is the same. It is that the simulation has RANs in some regions where RANs is best and LES would be too expensive because the boundary layer is too thin. And then LES in regions where RANs would get too confused. The principal distinction in these hybrid methods is between seamless and zonal methods. I prefer seamless when you have this complex of flow, a zonal method in which the user would pick, you know, X, Y, and Z regions to use RANs and to use LES. I don't think that's practical. Hybrid methods have what I call success stories that I'll show, but also some loose ends. From a theoretical point of view, we don't have a filter that we're really using. And the other one that people struggle with is that the seamless methods will switch from RANs to LES on their own, and sometimes they hesitate. So this is the flow that really explains why we need unsteady simulations. So it's a cylinder at subcritical Reynolds number, laminar separation. So the experimental CD is about 1.3. So you can run a steady RANS model, force it to be symmetric, and you get, you know, an honest solution, but the drag coefficient is much too low. So here we ran a 3D simulation and we showed it, sorry, a 2D simulation, and we showed it as if it had been over a length of the cylinder. So people say, but come on, this flow is unsteady, it has vortex shedding. So you can take the same model, do an unsteady simulation, and you get vortex shedding, and the frequency is good, but the amplitude of the lift is too large, and the mean drag is also much too large. You can do 3D URANs with periodic conditions in the third direction, and you get simulations that look like this. And in this case, we were very lucky with the drag coefficient, but the simulations depend too much on which turbulence model you're using, how wide the period is in your simulation. So 3D URANs, I don't think has a future. So now 3 cases of DES. The first two use the SA model with different grids. And as you go to a finer grid, you can see that the simulation is resolving more vortices, smaller vortices, more turbulence, and that gives you more accuracy. The part that you're modeling inside the LES is weaker and weaker. And here with the SST model, again a DES, it has even slightly a finer turbulence, but it looks quite the same. And that's really a strength of DES, is that it doesn't depend too much on the underlying model. This I call a big success story. NASA did experiments with tandem cylinders. So the turbulence of the first one would strike the second one and create a lot of noise. So you see the simulation with a very wide domain and the impingement of the turbulence, and there's really a lot of turbulence in here. Now, if you use URANs with different models, compare with the experiments, none of them give good results, and they're also very different depending on the model. In contrast with DES, the accuracy is much better, and you notice that this is quite a complex distribution. This is the root mean square pressure, and it's also very robust. It gives essentially the same answer with the ST or SST model and in different solvers. This was results of a large European project that was, I think, very successful. Another success story, the NASA wall-mounted hump that you can see here was created to cause separation. So we start with a steady round solution in the full domain, and there's a separation, reattachment. It's fine, but you'll see that it's not very accurate. And then we have two zonal RANS IDDES methods with the SST model again, in which we grow the boundary layer with RANS. Then we have a synthetic turbulence generator here that creates turbulence, and then the rest is essentially large eddy simulation with a wall model provided by DES. And the second run, this is all worked by the Russian team that I worked with so many years. The second one, we took a big risk and moved the boundary between the two pretty far downstream. And this is the result. Skin friction at top, pressure coefficient at the bottom. And you see that coming in, they all give the same answer. They tend to miss apparently a relaminarization of the experiment. But then the separation is not very difficult. Here, separation, the skin friction goes negative. But now what's really striking is how the RANS reattaches much too late. You also see it on the pressure distribution. And all the models do that. They miss some kind of an extra generation of turbulence after separation, whereas the two DES runs are almost identical and very, very close to the experiment. So this is a zonal simulation that is, not great for engineering, but it shows really the very, very high power of these turbulence resolving simulations. This is it. Thank you.